Hey folks! Okay, well, we've had a fair bit of fun playing with lists and recursion and different data structures. What I want to take a look at today is how lists are actually implemented in Lisp and the impact that has on how we use them. So, we've already seen a couple of cases where we looked at sort of shallow versus deep copies with lists, where if I make a copy of a list using just, def var L1, L2, then what we actually wind up with are two variables that are actually referring to the same list. And so if we go through and change the contents of a list, we wind up actually changing the contents of both effectively. And this actually has more implications when we start passing lists around to functions and having the functions do things to the contents of the list. You can wind up impacting the variable in the caller, if you like, as well as in the callee. And it starts looking a lot more like a pass by reference than a pass by value, if you like. So we want to take a look at why that's the case. So today we'll look at the gory details of list implementations. So for primitive data types, so the characters, the integers, the reals, the booleans, and whatnot, Lisp can set up a storage cell for them, if you like, a chunk of memory, just using a 32-bit or 64-bit chunk of memory. Right? That's no problem. But if you've got lists or strings or vectors or arrays or whatever it might be, then you've got a different problem, right? You have an arbitrarily sized something that you might need to keep track of. So for these, for lists in particular, Lisp takes a linked list approach. So what it actually does is stores a pointer to the front of the list rather than actually storing, the list itself. So if I create a variable L and assign a list to it, L is actually more like a reference to wherever that list is, which explains why when I copy, L1 to L2, I'm copying the pointer, really. So this allows a variable or a cell to hold a pointer. So again, we can start looking at, say, everything being 64-bit cells, where I've either got a primitive type or I've got a reference to something else. So for the lists, what will happen is each element winds up getting represented in two parts. Something that refers to the actual element, so if you like one of these primitives, and a second part that refers to the rest of the list. So if you think about our car and cutter, where it's grabbing you the front element or it's grabbing you the rest of the list, what it's really doing is either grabbing that first piece, that's the value, or the second piece that's a reference or pointer to the rest of the list. So if the rest of the list, if the element is actually a list itself, then the value of the element, if you like, is a pointer to the front element of the list. So let's try that with a couple of pickies here. So if I do something like create a variable L and I assign a list to it. So I've got this list 1, 2, 3, 4. Again, what's actually happening is L is going to be a reference to wherever the list cells are in memory, and each cell is going to have two parts: the value associated with it and a reference to the next cell in line. So it really does have kind of a linked listy type approach. So the head of the list, the car of the list is this one, and then a pointer to the rest of it. The cutter of the list is this pointer to the rest of the list, which again is going to go through cells, right? We've got in fact, a reference to this pair of cells that's got the second element and a reference to the rest, right? Which is going to have the third element and a reference to the rest, and a fourth element. And once you hit the end of the list, it's just a nil, right? An empty list. There is no more. So this is the structure behind the scenes that's being used. So if I do something like copy L to L2 or to X or something like that, then I'm just copying this front reference. Now, if I've got nested lists, so if I've got something like this where I've got a list whose elements are lists, so the first element is the list 1, 2, and the second element is the list 3, 4, then if we think about what this means, is our first element, right? So if I take L is referring to the thing as a whole, which is actually referring to the first cell. That first cell has the two parts, one that refers to that front element, which is in fact a list, so it's a reference to wherever that list is. And the second thing is a reference to the rest of the list, which is, again, going to have our second element, which is going to have a reference to that sublist, and then a null, right? Because there's two elements here. So if we're looking across the elements of L horizontally here, we've got the first element, and its cutter is pointing to the second element, and then there's nothing more after that. And then the elements, right, the cars of these are referring to the sublists, which in turn have a value for the element and a pointer to the rest, a value for the element and a pointer to the rest. So you do wind up with this very much a linked listy structure to our lists. And if you can keep this in mind when you're looking at the side effects and the weird and wonderful things that happen when you start manipulating list contents, this is how you explain it, right? Think about what the internal structure is, and if you change the car of the cutter of the cutter of the car of some list, you follow through and think about, okay, well, where is that taking me in this chain of pointers, and which is the piece that I'm changing? So if we think about setfs on cars and cutters, so let's say I define my original list L, that's a list 1, 2, 3, right? So I've got that first stage where L is a reference to the list 1, 2, 3, each has a pair of cells. And then I say, now let's change the car of L to 5. So this is essentially going through L and saying, okay, let's look at the front element in L and change it to the value 5. Okay, that makes more or less sense. Right? We're just changing that one value. The tail is still the same, so everything else is still okay. Now suppose I say, well, let's do a setf on the tail of L and just change it to nil. So now we're going through and saying, okay, let's go through L and look at, here's the cutter of L, right? It's basically just a pointer. And the cutter of the cutter is the next pointer along, and we're going to set that to nil. So we're essentially just chopping off access to that last element. So this is the kind of thing to think about when you're doing setfs, or when you write a function that does setfs somewhere within a list. So again, this is where our shallow and deep copies come in. If I do a shallow copy of a list where I create my list L that's just a 1, 2, and I create a second variable that I make a pointer to it. So actually this, so x in this case should be referring to the same as my list L. Okay, that red pointer is coming from this. So my def var xl, they're both going to be referring to the same thing. And then here, if I go through and say, now let's change the car of x to 10, then we're going through and saying, okay, well, let's go through and look at the front element of x and set it to 10. It's going to change it to 10 for both, right? Because they should both be referring to the same thing. Not quite sure where I got that red arrow from. Let's see, and then if I just go through and do a straight set f of x to 10, so if I'm not following one of my pointers, right, the car and the cutter are following pointers into the list, if I just simply change x to 10, that's going to have no impact on L. I'm just saying, well, instead of x being a pointer, just make x 10. Right? It has no impact on L. L is still pointing to this list that's somewhere off in memory. All right, so things to keep in mind when we're going through and playing with this. And again, this works when we're passing a list to a function as well. If I create a list and I pass it as a parameter to some function, then I'm passing a reference to the front of that thing. So if I've got my function f that's got a parameter x, and I go off and I pass L to f, then I'm saying, okay, so now f has got this x that refers to the front of L. If in function f I change x to 10, I'm changing this parameter to 10. I'm not changing the list, I'm just changing this parameter to 10. So it has no impact on the original L. But if I use x as a pointer to somewhere inside there. So if I say, well, I'm getting x, which is a reference to the front of the list, and I'm going to go through and follow that pointer to the inside and change what's inside to 10, then I'm going to go through and actually have an impact on L as well. So again, if you think about the underlying linked listy style implementation of this, it explains a lot of the behavior that you're going to see. Now, this is going to impact our use of cons as well. Suppose I have some list L that's, L's got 3 elements, 1, 2, and 3. And again, they're set up as this linked listy style. And then I create this should be a def var. I create a new variable x, and what I'm going to do is x is going to be the result of consing 4 to L. So again, L is a pointer to this 1, 2, 3 list. And so what I'm doing for x is I'm creating a new element that's got 4 and a pointer, and that pointer is to the rest of the list. So now x is a list that's got part of L somewhere inside it. So keep that in mind. So if I was now to take my x and go through and do something to the cutter of x, that's going to impact L as well. If I do something to just the front element of x, it's not going to affect L because L is only referring to the stuff after that. So you do need to start thinking about the underlying structure of the lists that we're creating. Now, one side effect of this is if you want to get really kind of warped, you can go through and create circular lists. So let's say I create this list L that's, the elements 10, 20, 30. And then I'm going to change the tail of the tail of the tail of L to L. So I'm making a pointer from that last element to the front of the list, essentially. If I look at the third element of L, then I'm going to go through and get the 1, 2, 3 element, right? It's changing. So instead of the third element being 30 here, the third element is now back to the front of L. So I grab the third element, or pardon me, the zero-based. So the fourth element is actually back to the start. And the fourth element is going to be 20. What we've got is this circular list where L points to the front element, that points to its tail, or the cutter points to the second element, and its cutter points to the third element, and its cutter points back to the front. So, very interesting. You can create these circular lists, but that also means that if you do something like try and print your list, so you try and do a format statement that prints the contents of L, that's going to get locked into an infinite loop, and you're going to see all this stuff scrolling through the screen as it prints the contents of L over and over and over and over and over and over and over. So, you can actually get around that, and you can tell Lisp to do cycle detection, and if it detects a cycle, don't try and print it. So you can there's a variable called print circle that is involved, so set it to true, and it will turn on essentially this cycle detection for our format statements. Most of the time, hopefully you're not creating circular lists, but we are going to run into a situation later in the term where we're dealing with environment variables that might already have circular lists in them. So when we come back to that point, remember, oh yeah, Dave said something about we could get into these infinite loops of printing. So keep this in the back of your mind. You can have circular lists in Lisp, and that is an issue when we try and print them. All right, I will leave that there for now. Again, keep the linked list idea in the back of your mind, and think of your car and your cutter as two fields of a struct, and representing a cell for our linked list, and we should be good. Okay, we will pick things up next time around.